Okay, good morning. The biggest surprise for me is that you're back, okay? Thanks for your confidence. So let's start with a quick summary. I see we've got a number of people online, and I promise you we're going to interact a little bit more than we did on Monday. I'm still learning how to balance all of this. So we're looking at systems of linear equations. So linear means there's no x squared, x cubed, sine of x, log of x, etc. Just x's and y's with no absolute values to the power of 1. And we mostly looked at 2 equations and 2 unknowns because we're doing everything by hand. And then we found out that depending upon the coefficients, we could have a unique solution, which means there's one and only one pair of x, y values that simultaneously satisfy the 2 equations. There could be no values of x and y that satisfy the equation. Or there could be an infinity of values because you're kind of in a degenerate case where they're parallel and they actually lie on top of each other. So you don't have enough information to distinguish a unique value.
You called back.
And then the other thing is...
Because I didn't want to wake you up.
You cannot have...
I know that.
Okay, do we need to mute anybody? Or is that just the room next door? Okay, so... You cannot have the case where there's exactly 2 solutions to the equation and not an infinity of solutions. Okay, so you can't have 2 and only 2. You can't have 3 and only 3. And that's independent of the value of n. So these pictures carry through to dimension 147, but that's really impossible to show with the notation that we have right now. And just to show you how graphs kind of break down very quickly, we'll just do dimension 3. So in your first homework, you'll have the joys of discovering some of the things of Julia. But I think what you can see here in the upper left corner is that I have 3 equations and 3 unknowns. The x's, the y's, and the z's are the unknowns. There's 3 equations. And then all I do is I solve for the value of z in terms of x and y in those 2. Okay, so that's just manipulation. But then look at the beautiful thing in Julia that you'll discover in the Jupyter notebook that goes with homework 1, is you can build these functions that look exactly like what you would write as a human, okay? So the mathematics is very easily transformed into equations. And then there's many different ways to do plotting. And we won't go through the details there, but they're there in the notes. But you know, you look at these 3 equations and 3 unknowns, and does it have 1 solution, 2 solutions, 3 solutions? Your guess is as good as mine. Oops. Undo. 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 Okay, now slide them up. So, how good is your 3D visualization? So here's the y values, here's the x values, here's the z-axis, and the D1, D2, D3 corresponds to each one of those equations, and we're plotting z versus x and y, and it's linear. So each of these is a plane. And so what we have here on the intersection is actually a line. Can you see the line? The black, but can you see it without the line, that there's actually an infinity of solutions there? There's the line. You can grind through the algebra if you want. Here's some different views. So it's kind of here, but it's still not, at least to me, super spatially clear that we have that. Here's a zoom, a little bit more clear that they actually intersect in a line. Okay, so what's the point here? Already in dimension 3, visualization is not the way to understand uniqueness of solutions, okay? We can do that with 2 equations, 2 unknowns, and then we see we have lines that cross, we have parallel lines, or we have lines that don't intersect. But even in dimension 3, that breaks. So what we're really after today is more powerful notation. We're going to introduce the notion of vectors, matrices, and then writing systems of linear equations in the form of a matrix times a vector of unknowns times a set of constants. Okay? Questions so far on what we've covered on Monday and the summary? Everybody good to go? So there was a question, was there short lectures, meaning Monty's videos that you're supposed to watch before a lecture? I would not use the word supposed. They're available if you want to watch them. I think they're very well done because they're very short. They're also maybe useful for once you've seen the lecture and you're just trying to review something. So maybe the quizzes come out and it's covering a particular topic and you can just click on the lecture that covers determinant of a matrix, something we'll cover on Friday, etc. So there's no demand on you that you read that ahead of time, watch the video ahead of time.
I just only saw that.
Monty, I guess the question is how many such videos are posted? I thought we had 3 posted up there, but maybe you can put in the chat and then explain on Piazza a little bit better, Monty, the availability of the videos, okay?
I think you can click like next lower left when the video finishes.
It's a playlist, so in order.
Okay, does anybody in the remote world have a quick question? You want to type that into the chat? Your mic is on. My bad, thank you. Okay, so we're policing each other in the remote world. That's cool. Anything else? Everything clear for everybody that's following the course remotely? Okay, thank you, Justin, for nodding. I appreciate that. And I will then go back to screen share. Okay. And Tribby, make sure I do this every once in a while because everybody should be feeling that they're incorporated in the class. And we'll try to figure out a way eventually where we can actually see each other, but right now, not. Okay, so here's the first concept is one of an array. So an array is just an ordered list of numbers. In principle, does not have to be numbers. It can be characters and strings. For us today, they're numbers, and by numbers we mean the real numbers, things like square root of 2, 1, 0.9994, etc. Real numbers. And here is an outtake of a spreadsheet, and we're very used to, I suppose, all of us have rows in our spreadsheet and we have columns in our spreadsheet. And that vocabulary actually comes from matrices and vectors. And then I don't have a picture of it here, but you can imagine that you take this spreadsheet that is, let's see, 20 rows and 1, 2, 3, 4, 5, 6, 7 columns. So it's a 20 by 7 array. And you can take that and stack it up with another one that has another 20 by 7 and just keep stacking those up into another dimension. And so this could have 3 indexes, rows, columns, and I don't know what else you call the next index, okay? And then you could have a 4th one, and a 5th one, and a 6th one. So in Julia, you can have as many dimensions as you want, as long as it's finite. There's no infinite number, remember, okay? So, and it doesn't like 3.5 dimensions, okay? It should be integers. Okay, so that's the notion of an array. So what we're going to be doing then is now building these things into vectors. And the first thing we'll get going is naming variables. So if we only had 3 things, it's very nice to use X, Y, and Z, but we want to get up to scale and have hundreds of things. So we're going to use subscripts. Y1, Y2, Z1, Z2. But it could be alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 218, etc. Okay? So we'll have variables, and this makes it really easy when we are programming because we will just index into the variable in an ordered way. So it'll become very natural when we start doing Julia in homework 1. So write down our first vector, V, and I chose these 3 magic numbers by going like this. Okay, they just magically came to me. So a vector is an ordered list of numbers, just like an array, but this is a column vector. Okay, it has 3 entries. It has a first entry V1, it has a second entry V2, it has a third entry V3. Okay. Has 3 entries. V1 is pi, V sub 2 minus square root of 2, V3, a very boring number 4. Okay, so that's a column vector, and there's nothing magic about 3, except I don't feel like writing a 17 vector for you, that's all. Now, the key thing here is the order matters. Okay, so what did I do here? So if I change the order to minus square root of 2, 4 pi, that is not equal to the vector pi minus square root of 2 and 4. Okay, they're different vectors. The order of they have the same entries if you look at the ensemble of them, the set, but they're not the same vector. So the order matters. So now we can also write it as a row vector. How about W? And I don't know, 1.6 minus 11, 2/3. Okay, so this is called a row vector. And just like with column vectors, the order matters, okay? Just as with column vectors, Okay, so row vectors, we write them in a row. Column vectors, we write them in a column. Sometimes we might say this is a 3 vector or 3 by 1 because it's 3 rows and then there's a single column. But we'll get to that in just a little bit. Order matters, and you can write a vector as a row, as a column or as a row. Great. Now here's just a heads up. So in many textbooks, and research articles, so it's not just textbooks, one might write W equals square root of 2, 1/8, 11 is a row vector. Now, I know the numbers are different, but if I look at how I wrote this row vector and how I wrote this row vector, is there a difference? Hey, anybody willing to volunteer what that difference might be?
The comma.
So the answer from the class is somebody noticed that W here, I put spaces in between the entries, whereas this one, I put commas in between the entries. So commas separated them. So it's very, very common. Okay. But this will drive you crazy initially when you start going to Julia, okay? So we'll remind you of it when you're doing your notebooks, etc. Me, when I'm writing in class, I will try to avoid this so that you don't get into a habit of it when you are programming, okay? If we were doing a course where we're using MATLAB, then it wouldn't matter because MATLAB takes commas and spaces to mean the same thing, but not in Julia, okay? So it's just a small thing. Okay. Now, suppose I have a vector and it has only one entry. Is that a row vector or is that a column vector? Answer, it's a trick question. It's both, okay? So, you feel better now because you're going like, it should be both? Yeah, okay, so is both a row vector and a column vector? So that's fine. Now, so this is just as another heads up. And we will get to it when we do Julia more. But for example, if I write a vector W equals 9, so in Julia, as soon as I put brackets around it and make it a vector, this is no longer treated as a real number. So you if you had a 9 and an 8, and I said multiply, you would say that's 72, because it's the real number 9 times the real number 8. Julia says, I don't know how to multiply vectors like you're telling me to, okay? And so it will then cause problems. So heads up, W equals 9 is different than the number 9. Now, if you were to find W1, and in Julia, the way you would do that is you would go W of 1, and then that would be 9, and that's just a real number. Okay, so there's a few little tiny things where Julia and common mathematical notation have nuances that will drive you absolutely bonkers in the very beginning, and then your brain does that snap, and then it's not a problem afterwards, okay? So I'm just giving you the heads up that you're going to be frustrated. I told you you're going to be frustrated. You said, no, it's so simple. I will not have a problem with that. I will not be frustrated. Everybody around me will be frustrated, but I will not be frustrated. But believe me. Okay, so that's just a small thing. Question?
So is Julia one index?
Is Julia what?
Starts from the index 1.
Oh, aha, we have somebody online who has used some of the C++ inspired, C inspired languages. Julia starts indexing at 1. MATLAB starts indexing at 1. So if you've had a course in C where you start indexing at 0 for arrays, then yes. Everybody who knows C thinks any language that doesn't emulate C is brain dead. Okay, that's how people feel. But hey, do you start counting how many times you go 0, 1, 2, 3, 4, 5, 6? You normally go 1, 2, 3. So anyway, that's how Julia does it. MATLAB does that. C and C++ start at 1. Other questions, Tribby?
No, they're just saying they're from EEX to 80.
Oh, so we have some people who are in EEX 280, and that's sort of going against this being a course for first semester students. Aha! We have somebody out there who's showing that they have more knowledge than we want you to have. Yeah, so if you're in EEX 280, yes, you're learning C, etc. How are we doing so far? Thank you. And how's everybody in the virtual world doing? I see a thumbs up from the one camera view that I see. And then Tribby's monitoring the chat. So, hey, thanks, Benjamin, for coming on and giving me the thumbs up. I appreciate that. Okay, so now let's go on from vectors to matrices. Okay, so A equals, and I'll write it as 1, 2, 3, 4, 5, 6, is a 2 by 3 matrix. Now, why do we call it a 2 by 3 matrix, for example? Because, like a spreadsheet, it has 2 rows and 3 columns. Okay, that's all it is. Okay, because it has 2 rows and 3 columns. Okay, so here are the rows. 1, 2, 3. There's 1 row. 4, 5, 6. Here's another row. Okay. Oops. Still, oops, there we go. Okay, those are the rows. And A equals, I should do this like this probably. 1, 2, 3, 4, 5, 6. And you're going to be totally shocked when I do this for the columns, okay? Let's call that rows of A, columns, rows. Okay. Let's do B. Square root of 2 pi, oh, I love E, 6 factorial. 47, 19, okay? That is a 3 by 2 matrix. Okay, so I won't bother highlighting the rows, but row columns. Okay. And just like with vectors, where you have the entries matters. If I swap the position of the 6 factorial and the square root of 2, that's a different matrix. Makes sense. Okay, cool. Now what about this? C equals 14, 11, 12, 2, 8, 13, square root of 2. What is that? Thank you. The answer from the class came back almost instantaneously. We had the transmission time of my voice, a little bit of processing time in the neural circuits of the student, and the answer came back. What is this? Wrong. Okay. And it's because we cannot have matrices with missing entries, okay? Missing here does not mean 0, it's just undefined, okay? So, wrong, because the second row is not filled. Okay. Now I know this seems like really kind of almost on the border of ridiculous to even write something like that down, but we'll circle around to this point in a little bit. Okay, so you have to fill in all of the entries when you're doing a Rob 101 matrix. Okay, so what does a general N by M matrix look like? Okay. Now this will probably challenge my handwriting. Let me replace that with 3 dots. Okay, so that has n rows and m columns. Okay. So n and m bigger than or equal to 1. They're finite. So we call this a rectangular matrix. N rows, m columns. They don't have to be equal. Okay, we'll come back to what the A11 and A12 means, but I've listed the rows as the first row, the second row, and the nth row. And I've listed the columns as the first column, the second column, the third column, and the nth column, okay? So you got a hint now of what the A117 would mean and the A411, okay? Then if I do A equals A11, A12, dot, 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 A1N, A1, A2, A, 21, A22, A2N, then AN1, AN2, ANN. So this time n equals m, we call that a square matrix. Same number of rows as columns, we call that a square matrix. Okay, let's just go ahead and ask the obvious, a little bit crazy question. Is a square matrix also a rectangular matrix? Yeah, okay, it's a special case of a rectangular matrix, okay, so cool. So all matrices are rectangular, but we usually don't call a 2x2 matrix a rectangular matrix. We say it's square, okay? You usually give it the most restrictive class that it's a member of. It's only normal. You know, we usually don't refer to ourselves as mammals. We are, okay? We're mammals, but we usually use a different label for the human race, okay? So that's all it is, okay? So that's the same thing, the genus of matrices, rectangular, square, and then later on we'll have diagonal and triangular and all things like that. Okay, so that's just a little vocabulary. So, whoops, what happened? I see. So what does the notation A sub ij mean? Okay, so it means it's the entry in the ith row and the jth column. Okay? Is an element on the ith row and jth column. Okay, so that's what that means. And so when I had A22, that's on the second row and the second column. A23 is on the second row and the third column. ANN is the nth row and the nth column. Okay, so that's how we index into them. In Julia, you just put square brackets I and J, as you'll see. Once again, homework 1 has all of this stuff, okay? but you index the rows first and then the columns. Makes a difference whether you put the columns first or rows, okay? They're different. Okay, so here's this. Suppose A is equal to 11, 14, minus 2, 8, square root of 2, and pi. Okay? Just make sure our notation is good. What are A12, A23, A31, and A13. And if you've already answered one of the questions, I'll ask you to let somebody else chip in. And you guys online, if you don't mind just punching into the chat if you feel brave. A12 is equal to, hey, thank you. A23, hey. A31 doesn't exist, it's not defined, okay. Okay, not defined. So in Julia, when you start indexing into indexes that don't exist, it gets very unhappy and you'll find out that you've made that mistake, okay? So that's good, that's good. And then finally, A13, hey, wow. You see, that's the kind of questions that might be on the quizzes and stuff. They're super hard, right? Yeah, we're ready for them. Whoop. Oh, pi, excuse me. I got too excited. I failed the quiz. Oh, 1-3, God, what am I doing? Oh. JWG failed, okay. Class passed, okay. It's tough. You'll find when you're up here, your IQ drops about 20 points, okay? So anybody doubt that, they can float up here and take over the lecture. It's so easy. I think any of you guys could be doing this right now. It's a matter of, can you make mistakes and still power on, okay? Okay, so now we understand indexes into matrices, vectors. We know that the order we put things in matters, etc. So let's start expressing linear systems of equations in the form AX equals B. Okay, so this is super important. Okay, so okay, because the problem is our usual way of doing things, and I'm just going to deliberately put all of the elements on the same side of the equation. Okay, I'm going to do that on purpose, just so that we can look at the general case and just handle it, okay? I'm going to write this in matrix form, and then this manipulating on a sheet of paper when you get beyond 4 or 5 equations. I mean, I think I've done up to 6 or 8 once because I really wanted to understand a problem. But when you get it written like this, we do equations with 10,000 variables all the time. Okay, so it just changes your life on what you think is a hard problem and what is an easy problem. Okay, so good notation. Okay. Any questions? Everybody's good? Yes, Tribby.
One comment is that they can't see when you point on the projector.
They can't see when I point on the board. Okay. And, okay. I'll try to avoid pointing on the board. It doesn't show up very well. Oh, I see, because they're getting this. And then the camera feed. Yeah. Okay. Yep. Thank you. Noted, and I will try to figure out a way to avoid that. And it'd be nice if I had something that I could highlight with here. So I'll work on getting that going.
My house teacher has like a in-camera feed of like him in the corner, so you can see like whatever he's doing and what's on the screen. I don't know if you can do that, but
Yeah, I don't know. We'll have to, Tribby and I will, yeah, any ideas, and we'll just try to make it better. So we just want this to be optimized. If we survive the first week, everybody's got enough information. We're going to go, there's only 13 weeks to go. Okay, so here's step 1.
Is that with the question mark over it? Is that just a line segment? Or
The question was, what is this messy thing that the professor just erased? And the thing is, we want to go back and forth. And the question is how to establish an equivalence between writing things out by hand in terms of variables and then writing them with a matrix, a vector, and another vector. There. So thank you for that question. Okay, so order the equations. Whoops, come on. As you wish. And stack. The unknowns into a vector. Okay, so for us, it's very natural to do x is x1 and x2. Okay? We'll do an example shortly where it's less obvious, and you'll see that you have total freedom in here. Here it's sort of almost imposed by indexing them as x1 and x2. So in principle, you could have put the x2 on top. It's your call. Now, what do I mean about the equations? So if I call this equation E.1 and this E.2, you know, I could swap those if I wanted and put E.2 on top. It's same system of equations, okay? Exactly the same system of equations, but we do that. Step 2, move all constants to the right hand side. RHS, right hand side. So typically we'll just write RHS and group you wish, stack them into a vector. Okay, let you catch up with the writing. Now, you already have these equations, so you don't need to write this. So let me make sure that that's the same thing. x1 plus x2, I bring the 4 on the other side. Yeah. And then 2x1 minus x2 equals minus x1. So I just stack those, the constants, into a vector. So we have two equations. We have two unknowns. Because we have two unknowns, we get a two-column vector. And then the constants in the equation, we put them on the right-hand side. Okay, so just a quick question. If I had, remember this was E.1, this is E.2. If I had swapped E.1 and E.2, then this vector would be -1 on top and -4 on the bottom. Doesn't change the system of equations, right? E1 and E2 together is what's defining our point in space where we have a solution. You write them down in your chosen order, but once you make a choice, it fixes what B is and it fixes the order you put the unknowns in X. So that's what's important. Order matters. Okay, so then step 3.
Mister, I had a question.
Whoops, sorry, question, yes?
Shouldn't the 4 and the 1 be positive?
It should be plus, yes?
The 4 should be positive.
Question from the audience is, did I get the sign wrong on 4? Yep. Yep. And I had it right in my notes. I should have been looking at it here, it's right, and over here it's right, and then I got it wrong when I did it anyway. So thank you for that. Other questions? Anything in the chat? We're good. Okay.
Could you scroll up to step 1 really quickly? I just
Did I?
It's to step 1.
Yeah, I'm not hearing the. Yeah.
Okay. All right.
So x1 plus x2 equals 4, 2x1 minus x2 equals -1. Yep. Okay, so how do we get the A matrix? And then I guess we're out of time, okay? So we form A by the ij entry equals the coefficient of x sub j in the ith equation. Okay, so let me write my equations down carefully. x1 plus x2 equals 4. 2x1 minus x2 equals -1. So we have almost everything filled in. So this is our B, this is our X. Let's fill in A. So the 1-1 entry of A is, drum roll, I heard a 1 from the class. The 1-2 entry, drum roll. We got 1 again from the class. The second row, first column, 2 from the class, and then the last one I'm going to fill in myself, and I think I get it right. It's a -1, okay? So there's the matrix. You just look at these, and you fill them in. And we are over time, so I stop the lecture here.